Right. Thanks, Scott, for the nice, scary introduction. So I hope not to show many needles so that you don't faint in front of the camera. So welcome, everyone, and we're happy to at least be online and hoping to meet you at some point in real person. So I will be telling you a little bit of what I've been doing in the last couple of years. And well, this slide has been standing for a while, so I think it makes sense to move now to the next slide. So this is a picture from last year with those students who could join last minute before the last snow of last year was melting. And you see there are bubbles everywhere, no needles. We don't use needles on the street. But what I want to share with you in the 15 minutes or so we have today is a new definition I'm bringing for the word engineer. And then, as I promised, I will be talking a little bit about how bubbles can replace needles. And then, well, on another occasion, I will be more than happy to tell you about my other lines of research. But for now, let's just focus on what is my vision as a professor here at the University of Twente. Well, I like saying that I like exploiting bubbles for good purposes, and I try to connect them to the United Nations Sustainable Development Goals. And I like to stress that I'm interested in doing applicable research, which sounds slightly different than applied research, meaning that I'm really doing my best to bring scientific knowledge that can be used into society in the shortest time possible. Of course, that is ambitious, and I have a few examples on how that is possible, but on a more strategic alignment, I'm doing my activities along two main columns. Today, we will be talking more about the one on the left, which is trying to inject without needles. On the right, you see other activities that stem more from my PhD work, which has to do with ultrasound and bubble formation. And these bubbles are useful for chemical processing. Now, what I want to first share with you is an idea that is now under review. And basically, I devoted myself the last couple of years to try to think, how can I teach my students to be better scientists, innovate, and innovation is a buzzword in many settings. So I tried to really boil it down to what could be useful for scientists, engineers. It doesn't matter, it could be physicists, could be even dentists, you will see in a moment. So I think the common factor that most people would agree is that, well, you need some sort of knowledge to be able to solve a problem. The second is a bit shady, and today we won't have time to discuss, and maybe in the Q&A, but persuasiveness, I would like you to keep in mind the positive connotation of persuasiveness, meaning trying to convince with good arguments and evidence that one idea is better, or you should try it at least. The third one, when it gets even a bit more squishy for most STEM scientists, is empathy, because there's some sort of well, bad image that many STEM scientists have of being nerdy, really lost in the clouds, not paying attention to societal relevant problems. But we don't need to enter the discussion right now. Just keep in mind that these three ingredients, if we combine them on the right proportion, I have enough examples to demonstrate that you can solve problems more effectively. And this applies for different disciplines. So it could be physics, chemistry, but could also be for valorization activities or even the legal aspects. So more than happy to share later on. Right now, I promise I will give my definition of what an engineer is. And well, maybe some of you already feel like you're an engineer, even though you might not have it on your diploma hanging somewhere. But I like to think of an engineer that blends all these three ingredients I mentioned. And well, obviously connecting a society, the ingenuity or the way to solve problems is connected directly to innovation. And what I think is more important, and maybe most of you agree with me when we sit in academia, is the teaching and the learning aspect. So we need to be able to learn new things. Otherwise, we will get just stuck with the knowledge we got when we were students ourselves. If this topic is interesting to you, before I move to the main idea, there's a book coming up soon. And well, I hope to tell you more. Just last thing here is that these ingredients, you don't need to have in top up the whole process. So I use in my classes sometimes examples on how at the beginning of a project, you might need to have more knowledge. And later on, when you decide to enter the real world, you might have to convince or persuade other people to join your team to give you money. And eventually, when you have a product, you actually have to persuade people to buy your idea. So these ingredients we can discuss later on are, I'm very excited when this book comes out and see what type of reactions I will get. Now, as we were discussing, Scott is afraid of needles, but good news for him, he's not alone. There are some statistics that about 1 in every 5 person is afraid of needles. And I think those are underestimated values, because what we have seen in the last pandemics is that never before so many people were forced to face the needle. So now these numbers are probably increasing. But what we have also from before the pandemics is that on a daily basis, we use 44 million needles. If you can think of the needle after being used, it's biotoxic waste, you need to reprocess it. Also to have it sterile, a lot of energy goes there. Once you finish with the needle, you have a lot of packaging and plastic, so that if we remove the needle, not only we will be able to solve the problem of people who are afraid of needles, many treatments that you will see in a moment would be better, but also the environmental contamination component of our health care system would be reduced. So the footprint would be reduced. So what you see here right now on this slide is a lot of people who are not afraid of needles, or they conceal it very well because they look smiley. So these are the team that has been working with me over the last few years. On the top left, you see people who are already doing other stuff, and on the bottom right left, then you see the actual team working with me. And it's multidisciplinary, multinational, well, like our Yon Academy in Europe. Now, I want to share a short video with you. I don't know how many of you would be familiar. I'm not sure even if the audio will play along. Doesn't matter, the text in the subtitles is there. And you see Captain Kirk entering, and well, Dr. McCoy giving him a needle-free injection. And then you might be wondering, so why, if this idea, even though it's science fiction from the past, is not mainstream today? And actually, the idea of needle-free injection is totally quite old, actually. Around in the 50s, they were using it in many areas. And in the 19th century, there was a French guy already doing it. But most of these commercial examples or successful examples have been focusing on what I call deep injection, large volumes. When I mean deep is in the skin, when you have to inject, for example, in the muscle, you sometimes need to deliver 1 milliliter. That has already some success in the real life, but from a technological point of view, has many limitations. So I'm trying to overcome some of them by trying to inject smaller volumes and then superficial into the skin. So this is a totally different engineering challenge. And why I'm interested in solving this problem is, well, you might be thinking of tattoos, could be recreational tattoos, but also for people who have wounds, you can camouflage the wounds, or patients after a mastectomy, you can redraw the nipple and you can increase the quality of life of all these people. Then, of course, you can think of vaccines, you can think of insulin injections. So the most advanced technology right now for diabetes care are insulin pump and artificial pancreas, but they rely on semi-permanent needles that need to be inserted in your skin. And then after a few days or weeks, you need to replace them. And then after a few months, the patient has a lot of scars, a big problem for the belly region. And besides that, of course, there are some, well, uncomfortable procedures like eye injections and also the allergy test for kids and also older people, that if we can do it without a needle, we could solve many problems. Now, the main problem with the needles is, besides the fear, is that, well, many people actually skip treatment just because of the needle. And there are some statistics that say that even people trusting vaccines, they really have to overcome the fear of getting a sharp object in their body or just losing control. So having somebody injecting something in the skin. So the whole thing about fear or phobia, depending on how you define it, is a lot more complex because it has a societal component. But if we can reduce the sharp components of the needle, then we are better off. And then, of course, even well-trained nurses and doctors every now and then by accident prick their fingers, which has very grave consequences for the health and the economy, because these are people that if they are in a max vaccination, then they need to go home, take a few days, receive special treatment. So undesirable. If I would be in the classroom with you, I will ask you, like, how many of you have tattoos? And apparently the statistics are also underestimating that about 20% of the European population is tattooed. So why I'm showing you this is like to show first how a tattoo needle works. Let's see if the video plays here. So basically you just hack the skin, and this is porcine skin. And why I'm showing this is because, well, tattoo machine has been used to vaccinate and to do some of the medical procedures that I mentioned earlier. But one of the big problems with the tattoo needle, besides the classical problems of the needles and the stigma, is that you leave a wound behind. So how we're trying to overcome this is by heating with the laser a small container with liquid, and then a small bubble grows, pushes the liquid out of the microfluidic device as velocity is high enough to break the skin. So visualizing how to inject the skin is a bit difficult, but we have here a droplet, like if you would be having now a small droplet pending from a pen, then you will see here the microfluidic chip with the liquid on the left, and we're going to shoot at that little droplet. So it was too fast, so probably none of you really saw what happened, so I'm rewinding. And then you see here that in less than a millisecond, we really pierce through the droplet, and well, you see some of the red dye we leave behind. So we are now really able to control the velocity so that if you have less velocity of the jet, the whole liquid remains in the droplet. And to play a bit with the properties of the droplet, we put some polymers to make it a bit viscoelastic, and you see how the jet tries to escape, but then we pull it back. So I'm going to play it again for you. Why we're using polymers is because, well, skin is actually a viscoelastic material. So as some sort of a step in that direction, we are trying to understand how the impact of these small jets causes damage or deformation on different objects. From a different angle, you see like the Death Star from Star Wars being exploded. And we published recently a paper making some analogies about this. Now, this all looks very nice for academic settings, but well, how is it in the real thing? So most bioengineering studies on a needle-free injection use gelatins or agarose to first get a feeling of what is happening. So what we do here is replace the droplet by an agarose slab, and then you see here a non-efficient injection because you see here some splashback happens. Then the hole in the gelatin closes before the whole liquid gets through. So this is not an effective or efficient injection. The splashback is associated to cross-contamination, and you don't want to transfer material from one place to the other, even in your own body. Now, what we've been doing from our knowledge base is using microfluidic engineering tricks to play with the geometry of the chip, the fluidic properties, and now what you will see here is a slightly better, almost optimized injection, where again, in less than a millisecond, you will see how the liquid gets inside the gelatin without the splashback. And most of the liquid will be able to get through that tiny hole before it closes. And we're talking here about 1 millimeter injection depth approximately. Now, what happens in real skin? Right now, I'm showing you here some slides with porcine skin. We see that, well, the penetration is obviously modest because, well, skin is a little more complex. And our assumption was that we will make a tiny hole, but to our surprise, we didn't actually see that hole. So there are two hypotheses. It's so small and it's already good because if there's a wound, it will heal fast. Or maybe the liquid is making some sort of percolation through the interspace between the cells. Now, the applicable research part comes from the fact that we have applied for a couple of patents and we have created a company that in the future should be able to incorporate all this knowledge and have like a handheld device that would look like something similar to this, which you could use to vaccinate, to inject, or tattoo. That is my alarm. And well, I have a broader organization here to try to bring together different stakeholders. There's some YouTube information for that, and I will send you the slides. So if any of this is interesting for you, more than happy to discuss further. Thank you very much for your time.
Thank you very much, David. We have time for questions, so 3 or 4 minutes. Are there any questions? You can raise your hand or you can just blurt out. Martin has a question.
Thanks, David. Super nice technology. And I just learned that you're actually pretty close by to where I am in Nijmegen.
Okay.
And you pointed towards an application for vaccination, and that's sort of overlap with what I'll be showing later. But I have a question about the design, because it looks like between your microfluidics device, I assume it is, or you mentioned it is, and sort of the injection site or non-injection site. How do you call it?
I don't know, the target, the tissue, or
yeah, there's some kind of space. And also in your device design that you showed, there's also sort of a covered space between. So why do you need that space, and why can't you just put it directly onto the tissue, for example?
Well, there are two answers to the question. The scientific answer is basically, at the beginning, we're trying to understand the fluid mechanics, and well, that space gives us a bit of a feeling of looking at how the droplet breaks up in different liquids. Now, from a practical point of view, that is also desirable, because some injectors in the past have worked like really putting the orifice directly in contact with the skin, but then those jet injectors, the traditional ones, trying to inject large volumes deep into the skin, typically have so much power that the liquid, if you don't have it with the right alignment, eventually you can splash back and also can perfuse layers that you were not intending to inject. Now, while we use the spacer, has double practical meaning. The first one is that when you press with a given spacer on the skin, you apply a bit of a pre-tension, so you have a bit more reproducible way to inject that is not so depending on the orientation. And the second one is that if for any reason we have some splashback, having this sort of spacer, like an enclosed container, keeps all the drug there. If we're talking about some sort of radio label marked medicine or stuff like that, you want to make sure that everything stays there and you don't have aerosols flying around.
Great, thanks.
Are there other questions? We probably have time for one or two more. I have a few. I wanted to Monique has one. I want to discuss catalysts and bubbles at some point with you. Okay. She wants to discuss this with you later, David.
Definitely.
Is there maybe you were talking about 44 million needles a day. Is the needle industry against you? I mean, you said that there's this as a science fiction idea, it's been around for, or even as a practical idea, it's been around for over 100 years, but it hasn't taken hold. Are there certain inertias or institutional reasons why we wouldn't go to this? I mean, or has it just been, is there just a big 100-year gap in research on this, or what?
Well, I mean, it's a compounded result, and definitely there must be some sort of fear of the disappearing needle. So my approach is being actually quite open for collaboration. So big companies might see a risk here. The first, I'll say, quieting remark I would say is that we are not interested in replacing all the needles, because there are some treatments that already work very good with the needle. So there's no real need to change it. And you know, the medical sector is very conservative, and I can understand. So there are some things that if you have gone through the whole process of verification, validation, you don't want to just throw it right away. What I'm trying to make sure is that there are some treatments where it's demonstrated improvement in the effect when you inject intradermally over a larger area. So that doesn't need to antagonize directly with the needles manufacturer, because then if we create some sort of joint venture, then they can just increase their portfolio of products. So if they are smart enough and they team up at early stages with me, then we have a faster solution.